is not provided, it's automatically 0, is it?
Yes, correct.
All right, so thank you.
No need to assume tau m equal to 1. When the information is not there, you already screen the description. There is no information about the tau m, the measurement time constant, then do not assume s equal to 1. Just put 0. Okay, I think it's better for me to highlight one of the example for the tutorial just to have a clarity because in this case, based on my observation, there are some tricky part on the offset calculation. So we will take a look one example. So let me share my screen. Okay, here is the question based on the tutorial. So before this, we just to revisit, we already have the description of your condition where the GP is there, the GD, the GV, the GM, KM, set point. And we already developed the closed loop transfer function for set point changes. And I already highlight the calculation for offset when your KC equal to 1 and 10. And then the controller setting for P controller to eliminate the offset. So this one has been discussed. So in this case, if you take a look, there are two ways to calculate the offset. Not to calculate the offset, how the offset can be used. The first one, either we give you the KC value, you calculate the offset. That is the straightforward. We give you the KC value from the overall closed loop transfer function, you calculate the offset. So for the D is reverse. It's a reverse approach where we provide the offset value. In this case, the offset equal to 0, you determine the KC. So make sure you're familiar with this kind of calculation. Sometimes the question is not direct. They have some tricky part. So for this part, for this kind of equation, it's a reverse way. Why I call it reverse? Because we give you the offset value, then you do the back calculation to find the KC. And lastly, for E, calculate offset. This is the thing that I would like you to complete. All right. So in this case, I just, based on my observation, based on your submitted, for those who already submitted to me, I found this one is a little bit tricky for you. So let's have a discussion a little bit for calculate the offset. All right, like now, in this case, I highlight the using PI control. So I highlight using the PI control just for all of you to have a clear understanding. So for this part, we have the y prime s over y prime SPS. Okay. Equal to Km bar GC GV GP divided by 1 plus GM GC GV and GP. So this is the set point change problem. Because why I use this one, you need to take a look on this statement, set point change problem. And then they also give you a unit step change in set point using PI, PID, PD. So where the controller parameter is given, KC equal to 1, tau I equal to 1, tau D equal to 1. So meaning that in the previous exercise, in the previous question, where the KC tau I tau D is not given, then you need to have your answer in terms of expression. So this is the thing you need to understand. If no value of KC tau I tau D is given, then do not assume it. Just leave as it is based on your expression. This is based on the question question A2, if I'm not mistaken, for this question. So for the question A2, 3, 4, there is no controller parameter. So that means this kind of question just require you to develop the transfer function. So you need to have the answer in the form of expression. So back to our question again. So this is the set point changes problem where in the previous exercise, we already determined the value of your transfer function. So here, let me... So somebody can tell me what is your Km bar? Anybody?
Four.
Km set point is 4. And then what is your GV?
One, sir.
1, all right. The GP? What is your process transfer function?
5 over 5s plus 1, sir.
5 over
5s plus 1.
5s plus 1. All right. And then in this case, the GM?
GM is 1 as well, sir.
1.
1, all right. Thank you. So based on the previous calculation, your set point transmitter is equal to 4. The GV, the valve transfer function equal to 1. The measurement transfer function equal to 1. And your GP equal to 5 over 5S plus 1. And in this case, the controller that we are going to use is the PI control. So that means your GC has a following expression. GC equal to KC in bracket 1 plus 1 over tau IS. Where in this case, the value of KC and tau I are given. So you can substitute the value where the KC equal to 1. And then 1 plus 1 over tau I is 1. So 1 over S. So meaning that here the GC equal to 1 plus 1 over S. So this is your transfer function for PI controller based on the value substitution. So what you need to do next is the substitution into the overall equation. So y prime s equal to y prime SPS equal to the Km bar is 4. Your GC now is 1 plus 1 over S. The GV equal to 1. The GP is 5 over 5S plus 1. Divided by 1 plus the GM equal to 1. The GC 1 plus 1 over S. The GV equal to 1 and the GP phi over phi S plus 1. So this is the value substitution into each transfer function involve for set point changes. So the next step is just to expand a little bit the equation. So this contribute to the y prime S over y prime SPS equal to, so here 4 multiplied by 5 you get 20. 1 plus 1 over S and then you have 1 over 5S plus 1 divided by 1 plus 5, 1 plus 1S, 1 over 5S plus 1. All right. So this is the value substitution. So in this case, just for your information, we don't need to do the further expansion. So it does not require for you to try to expand the equation and try to simplify the equation. If you leave as it is, then it is okay. Normally, what I recommend is to just leave as it is. Because here we don't want you to do the further expansion because we want for you to reduce the mistake. Sometimes the most common problem when you try to expand the equation is possibility of you doing the mistake tends to be higher. So I recommend just to do the simple expansion. If you have this kind of the equation, you just multiply 4 times 5, 20, then it's okay. You do not need to rearrange the numerator or denominator. Just leave as it is. That is my recommendation. It's very, you quite lost if you try to simplify it. So in this case, we just leave the equation as it is. So now we want to calculate the offset. So here the offset equation is similar. Y prime SPS minus Y prime. Oh, sorry, not S anymore. Y prime infinity minus Y prime infinity at time infinity. So this offset calculation only able to calculate the value of the measured at final time. This final time refer to the time equal to infinity. So based on the given question, you can see the step change for set point is a unit. So here you have the a unit. So that means it's refer to the 1. So this information is given. Let's say the information is not given, then you can do your assumption. Of course, the simple assumption to assume magnitude equal to 1. That is the common understanding. So in this case, a unit step change in set point has been used. So that means the y prime SP equal to 1. So if we try to Laplace it, y prime SPS equal to 1 over S. So that is the expansion. So now in this case, we know that y prime SPS equal to 1 over S. Now we want to find y prime infinity. So in this case, we rearrange y prime S equal to y prime SPS multiply with the equation 1 over 5s plus 1 divided by 1 plus 5, 1 plus 1 over s, and 1 over 5s plus 1. So we have rearranged the equation for y prime s like this. So we know that the y prime sp in this case is 1 over s. So we can do the substitution. 1 over s, we replace it here. So in order to solve the y prime s into y prime infinity, we use the final value theorem. So for the final value theorem, when we want to find y prime infinity, the limit set is s become 0. That is the condition of final value theorem, and it is standard. We just use as it is. When time equal to infinity, s becomes 0. If you use t equal to 0, s become infinity. That one is what we call it initial value theorem. So that is the difference. Final value theorem and initial value theorem. So for this part, we just use final value theorem in order to determine the y value at time equal to infinity. So based on this, the formula is s multiply with the 1 over s multiply with the 20, 1 plus 1 over s, 1 over 5s plus 1 divided by 1 plus 5, 1 plus 1 over s, 1 over 5s plus 1. So according to this, the s becomes 0. So for this part, initially the s here and 1 over s can be eliminated. And whatever the s you have here, the s will become 0. 5s becomes 0. 5s becomes 0 and the s becomes 0. So if we try to take a look on this case, let me further rewrite it. Y prime infinity. So 1 over s, and s has been eliminated, so it become 1. Multiply with the 20. 1 plus 1 over 0. And then for 1 over 5s plus 1, it becomes 1. So 5s becomes 0. 0 plus 1 is 1. 1 over 1 is 1. Divided by 1 plus 5. 1 plus 1 over 0. Multiply with 1. So this is after we substitute the value of s with 0. So what happened in this case is we want to find the value of y prime infinity. So the problem here, when we take a look, in order to obtain the value is the 1 over 0. Technically, if you try to calculate 1 over 0, what is the value? What is the value when 1 divided by 0?
Math error.
Math error. Why it become math error? So in this case, just to make sure, there will be common understanding. If you have 0 divided by 1, automatically this one becomes 0. So what if 1 divided by 0? If we try to calculate it, it becomes an error. So based on the mathematical expression, when we have 1 divided by 0, this one become infinity. So this is the common understanding in the mathematical formulation. 0 divided by 1 is equal to 0, but 1 divided by 0, it become infinity. Why it become infinity? So normally in this case, if we notice, let's say we take a look on the alphabet A to Z, A to Z. So the initial alphabet will be A. The final alphabet will be Z. That is the clear understanding. But in terms of the numbering, there's a little bit problem. Because of course, if we take a look, our starting point is 1. Then the 1 itself, number 1 considered as the initial value of positive. Initial value for the positive number. But for the last positive number, in this case, it is never ending. Let's say you put 1,000, after 1,000, you have 1,001. If you put 10,000, then after 10,000, you get 10,001. So there is no clear understanding what is the final number. So the mathematical person in charge declare that the final value of the number should be infinity. That is the final value. There is no after infinity. This one you can check YouTube for why infinity considered as the final number. Final location of the number. It's like Z for the alphabet. After Z, you don't have any alphabet anymore. So in the case of numbering, infinity considered as the last number available. That has been declared by mathematical person. So what is the impact of having 1 divided by 0 inside our equation? So we take a look. So now we have 1. Y pi infinity equal to 1 multiply with the 20. 1 plus infinity. So here 1 divided by 0 is infinity divided by 1 plus 5. 1 plus infinity. So it becomes like that. So in this case, the problem is, since we consider the infinity is the last number, so whatever you add or you multiply still become infinity. There will be no after infinity. So meaning that in this case, 20, 1 plus infinity divided by 1 plus 5, 1 plus infinity. If we take a look on the numerator, 21 plus infinity will be approximately infinity. 1 plus infinity become infinity. Infinity multiplied by 20 still infinity. And the same goes with your denominator, the bottom part of your equation. 1 plus 5 in bracket 1 plus infinity also approximate to infinity. So in this case, y prime infinity equal to 1 multiplied by infinity divided by infinity. Remember that the infinity considered as the last number. There is no number after infinity. So that means if you add or you multiply, still you get the infinity. That is the concept. So for this part, that's why 20 multiplied by 1 plus infinity, you get infinity. 1 plus 5 in bracket 1 plus infinity still considered as infinity. So when you have infinity divided by infinity, this contribute to the cancellation of infinity, which will become 1. So this one is like the number. You have the same number on the top and the bottom, on the numerator and denominator. So it become 1. You can cancel each other. So meaning that in the end, the y prime infinity equal to 1. So the answer for y prime infinity for this case equal to 1. Any question? So if there is no question, then we go for the offset. So now the equation of the offset again equal to y prime sp infinity minus y prime infinity. So here the y prime sp infinity is equal to 1 minus 1. So your answer should be 0. 0 offset. This is
Sir,
the, yeah.
let's say if the y prime infinity is like answer is infinity or 1 equals to infinity means if 1 minus infinity equals to negative infinity or infinity.
Infinity only.
All right, sir, thank you.
Usually the number should be infinity. So for this part, you get 0 offset. So in this case, if we take a look, this is for the proportional integral controller, PI controller, where you have the GC equal to KC 1 plus 1 over tau IS. So the reason why you get 0 normally coming from the 1 over tau IS. So in this case, when you have the 0 offset means the process can be maintained at the required value, which is your set point. Let's say you want to maintain the temperature at 500 degrees C, you use the PI controller. In the end, of course, you will get the offset equal to 0 because the presence of the integral. So based on this equation, you can see the main reason you get infinity is coming from the 1 divided by 0. So 1 divided by 0 here coming from the integral part. So in this case, this indicate that the integral able to eliminate the offset is the main cause why you get 0 offset. So in the real application, if we want to maintain the process at desired value, we use PI control. That is the theory. This is the thing that you need to understand. Whatever the value you use for the PI, in the end, you will get the 0 offset. So this is the advantage of using PI controller. The limitation, because here the offset only calculate at time equal to infinity, or we can say at the final time. Whatever happened in the middle, from the beginning to the before it reach the end, we don't know. That is the limitation of this offset calculation. because you just considered the offset at time equal to infinity. How about at the middle time? We don't know. That one we need to do the full scale of simulation to find how the pattern, how the trend. So any question so far? Alright. So in this case, I already show you the set point changes for PI controller. So for those who already submitted, please correct based on this discussion and complete the PID and the PD based on the following approach. So now we go for the next question. Disturbance change. Alright. So for this one, I also highlight it for the use of PI controller. So for this part, this require the disturbance change by assuming a unique disturbance change using PI, PID, PD. This is the controller parameter value where the Kc equal to 1, tau I equal to 1, tau D equal to 1. So for this part, we just repeat the same thing. Only in this case is highlight the disturbance change. So for the disturbance change, normally you will have Y prime S over D prime S to highlight for the disturbance change. And then we have the GD divided by 1 plus GP, GV, GC, and the GM. So this is your disturbance transfer function. Disturbance change transfer function. So we just use as it is. The GP, we use the same thing like before, where the GP is based on the following information. I just copy. So we have the GP. All right. So we have the value of the previous example. Km bar equal to 4, GP equal to 5 over 5s plus 1, GM equal to 1, GV equal to 1, and the GC by substituting the KC1 and tau I1, you get like that. And lastly, you require the GD, the disturbance transfer function. So what is your GD? Disturbance transfer function.
One over 5s plus 1, sir.
Again.
1 over 5s plus 1.
All right, thank you. Thank you very much for the response. So now we have the GD 1 over 5s plus 1. So based on the disturbance change, we use the GD. And then in this case, we don't use the Km bar. So the GP, the GV, the GC, and GM is still the same. So we just substitute inside the equation. So we have Y prime S over D prime S equal to GD. GD is 1 over 5S plus 1 divided by 1 plus GP. GP is 5 over 5S plus 1 the GV equal to 1, the GC 1 plus 1 over S, and then the GM is equal to 1. All right. So we just substitute all of the given transfer function inside the disturbance change problem. 1 over 5s plus 1 is your GD. So this is your GD. This is your GP. This is your GV. And this your GC. And this is your GV. All right. So we have included all of the relevant transfer function. So in this case, you can do a simple expansion. Like I said before, you don't need to do a detailed expansion. Just simple simplification and expansion, just enough. This in order to make sure we reduce the probability of making mistake. So for this part, if you have like this, 1 plus 5 over 5s plus 1 and 1 plus 1 over s. That is enough. No need to do the further expansion. So here we want to determine the offset. So based on the calculation here, this one required to calculate the offset for disturbance change. So again, we use the same formula, offset equal to y prime sp infinity minus y prime infinity. All right. So here we have to find the y prime infinity value. So again, we use the same final value theorem. And for that final value theorem, we know that the equation y prime s equal to d prime s multiply with the 1 over 5s plus 1 divided by 1 plus 5 over 5s plus 1, 1 plus 1 over s. So in this case, if we take a look on the question, assuming a unit disturbance change. So the value, the magnitude for the disturbance has been given, which is equal to 1. So for this part, similarly, the d prime s equal to 1 over s. For this part, we employ the same method to find the y prime infinity using final value theorem. So based on this, y prime infinity limit s approaching 0 equal to s multiply with the 1 over s multiply with the 1 over 5s plus 1 divided by 1 plus 5 over 5s plus 1, 1 plus 1 over s. Alright. So this is the rearrangement of the y prime s equation where now we adopt the final value theorem. So in the final value theorem, the limit s approaching 0 when the time equal to infinity. So for this part, again, we try to eliminate the s, multiply 1s, you get 1. The 5s here, it becomes 0. 5s becomes 0, the s becomes 0. So based on this based on value substitution, then it become 1 multiply with the 1 over 5s plus 1. Since the s becomes 0, so 1 divided by 1. So in the top, you get 1. And in the bottom, 1 plus 5, 1 plus 1 divided by 0. So you get this. So still 5 over 5s plus 1. 5s becomes 0. 0 plus 1 become 1. 5 divided by 1 is 5. And then based on this, we can declare y prime infinity equal to 1 multiply with the 1 divided by 1 plus 5, 1 plus infinity. It's like that. And lastly, for this part, y prime infinity equal to 1 multiply with 1. So 1 plus infinity is infinity. Infinity multiplied by 5, still infinity. So the denominator for this equation should be infinity. Since we consider the infinity will be the last number, so whatever value you add, whatever value you multiply with the infinity, is become infinity. So for this part, that's why the denominator become infinity. So here, what is the value 1 divided by infinity? Anybody? What is the value 1 divided by infinity?
Zero.
Infinity.
1 divided by infinity, not infinity, but is approaching 0. Just imagine 1 divided by 100 is 0.01. 1 divided by 1000, 0.001. 1 divided by 1 million, 0.0001. So it's approaching 0 because infinity is considered a big number. So 1 divided by big number, normally the value should be approximating 0. So for this part, 1 multiplied by 0. So you get 0. Any question?
Doctor,
Yes?
so means that if 1000 divided by infinity also 0.
Yes, correct.
Okay.
Uh-huh. So in this case, let's say you have 1 divided by infinity is clearly approaching 0. If you have 100 divided by infinity or 1000 divided by infinity, all of this contributing to the 0 also. Because we don't know what is the value of infinity. It's not like that 100 divided by 1 million or so on. So here is maybe larger than that. So the best way to estimate 100 divided by infinity or 1000 divided by infinity, we approximate it as a 0. So that is the simple way. So now, any other question? Can I proceed? Okay, now I proceed with the offset calculation. So here the offset, if we recall, offset equal to y prime sp infinity minus y prime infinity. So what is the value of the offset? What is the value of your offset?
One.
How do you get one?
Because the y infinity will be 0.
So the y prime sp infinity, you put 1 minus 0. It's like this. Anybody else? What is your offset? You get 0. So what is your value? So that's mean y prime sp infinity is 0.
Yes.
0 minus 0 ah.
Ah.
Okay. Any other answer? Any other answer? All right. Thank you for your response. So based on this, we have two different answer. First one is offset equal to 1. And another, your friend answer offset becomes 0. So we want to observe which one is the correct answer. So for this part, I hope all of you listen clearly. So in this case, just to revisit, we already calculate two offset. The first one is based on this question, the PI controller for set point change problem. Set point change problem, we calculate the offset, where the offset now 1 minus 1 equal to 0. So that one, this offset is for the set point change problem. And the second question relate to the disturbance change problem. We use the disturbance change equation, we calculate the offset. So in this case, we know that y prime infinity is 0. So here the question is, what is the offset value for disturbance change? And your friend has two answers. Your friend provides two answers. The first one, offset equal to 1, and the offset equal to 0. So for this part, we still use the same offset formula, y prime sp infinity minus y prime infinity. So for this part, since this one is the disturbance change problem, disturbance change problem. So if we take a look on your slide, let's refer to your slide. Okay. Feedback control. So if we refer the definition, set point and disturbance problem. All right, here. So in this case, based on this slide, you can see there are set point changes and disturbance changes. When the set point changes is considered,
Doctor,
yeah.
We are seeing the Microsoft slide only.
Okay, sorry. Thank you for
Okay.
correcting me. Wait. So we refer to the notes, to the slide. Can you see now?
Yes, doctor.
All right. Thank you for correcting me. Alright, so if we recall, this is the overall closed loop transfer function where we have two problems, set point changes and disturbance changes problem. For the set point changes, this is the equation that we are going to use, y over ysp. Based on the definition of set point changes, the ysp cannot be 0, but the d equal to 0. The disturbance is neglected. That one is for the set point changes. For the disturbance changes, in this case, the set point change is neglected. Disturbance change, in the disturbance changes, the set point value will be neglected. So meaning that if we go back to your answer here, that's mean when we neglect the set point changes, so the offset calculation should be like this. Offset equal to 0 minus 0. So the answer should be 0. So this is your answer for disturbance change problem. Again, I repeat, this one is for the offset calculation in the case of disturbance change. In the disturbance change, we neglect the set point value. So when we neglect it, that means y prime sp infinity will be neglected, or in other words, become 0. That's why for this part, you can see y prime sp infinity contribute to the 0 answer. And for this part, the y prime infinity calculated is 0. So 0 minus 0 equal to 0. So this is the final answer for disturbance change problem. Any question? So just to revisit, set point change, problem, offset equal to 1 minus 1 equal to 0. For disturbance change, also you get 0. What it means? What is the explanation on it? So if we take a look, let's say we want to draw the sketch. So this is your set point value. And this is your test point, where the offset is 0. So this indicates that PI controller is able to maintain the process at required set point value. While rejecting any disturbance. So this is the feature of good controller. The good controller must able to provide 0 offset and also eliminate any kind of disturbance value. That's why in this case, your offset for set point change equal to 0. So this means the controller able to maintain the process at required set point. And for the disturbance change, the offset also 0. So this means any kind of disturbance can be eliminated by PI controller. So this is the thing that we prefer about PI control, because the presence of your integral contributing to the zero offset. So this is the thing you need to understand. The concept of the PI controller normally able to eliminate the offset. So when we prove how we know that, we prove by doing calculation. We use offset calculation as our evaluation. We employ the set point change, we employ the disturbance change. Based on the calculation, we obtain 0. So this 0 indicate that the PI controller not only able to maintain the process at desired value, but also reject or counteract any kind of disturbance value. So this is the explanation of your answer. So I open to any question that you may have. All right, if there is no further question, we take a break for a while. And after 5 minutes or 10 minutes, we continue our lesson. All right. So let's continue for our lesson today. So right now, I do hope you may complete the rest of the tutorial question. So in this for today class, you can download the material in the WhatsApp group or in the Google Classroom. So this is the topic for today, which is the stability of closed loop control system. So for this part, we want to observe how your process respond. Sometimes you may get zero offset, but maybe it will provide unstable system. So before we go for it, we take a look on what is mean by stability of closed loop control system. So for this part, normally the general stability criterion is based on the process response. We can take a look on the transfer function. So let's take a look on what is mean. Let's give you simple example to get a clear idea. So let's say we have the transfer function in the form of the first order, 1 over 5s plus 1. So for this part, since this is the first order, normally you get this kind of response. It will increase and steadily maintain. The first order response, normally you will have the steady increment until the process reach final value and become steady. So this is what we consider it stable. Because the process will not violate from the value. So if we don't sketch the graph, we can take a look on your denominator where you have 5s plus 1. We find the root of your equation, the roots. 5s plus 1 equal to 0. So you get s negative 1 over 5. So when you have negative 1 over 5, this means that the root is negative. Negative root contribute to the stable system. You will have a stable system automatically. It is the standard way to determine the process. So another example, let's say you have the GS equal to 5s minus 1. 5s minus 1. So if we calculate the root, the 5s plus minus 1 equal to 0, the s equal to 1 over 5. You have the positive root. So when we have the positive root, that means this normally considered unstable system. Negative root, stable. Positive root, unstable. So how do unstable looks like? So normally when you have the unstable, it becomes like this. The response is keep increasing or oscillating. And it never reach steady state. So this is the thing about unstable response. So for the closed loop system, normally what we want to achieve is stable. So the process not only maintained at the set point, which is providing the zero offset, but also to ensure we get the smooth response, where the response becomes stable. So this is what it means by stability. So for general stability criteria, normally the location of the poles. In this case, what is meant by location of the poles is the root. The root. So the poles normally at the denominator. So like I give you the example before, gs equal to 1 over 5s plus 1. So s negative 1 over 5. So this is considered the location of the poles. The root itself sometimes is called as a poles, where it's located on the denominator. Sometimes when we want to include the transfer function, the closed loop transfer function, it involves the GC, the GM, the GP, the GP, so many transfer function. Then it will contribute to the many roots depending on the complexity. If you have the pole with positive real part, automatically the system become unstable. To make sure all of the process become stable, all of the pole must be located on the left hand side, which is negative side. So this is the stability region, where when you have the stable region is on the left. So this means negative root. If you have positive root, then automatically the process become unstable. So we want to make sure our process is become stable by ensuring the root is negative. So if we want to apply this stability concept on our closed loop, so let's look on the stability of closed loop system here. Let's say this one is considered the standard block diagram. So based on this standard, we know that we have the KM, the GC, the GV, the GP, GM, and the GD. And where based on this, we take a look on the overall closed loop transfer function, Y equal to KM bar GP, GV, GC over 1 plus GP, GV, GC, GM. YSP plus GD over 1 plus GP, GV, GC, GM. So this is your overall closed loop transfer function. So like we have discussed before. So in order to make sure we evaluate the stability of closed loop system, normally we just use the denominator. So the denominator in this case is 1 plus GC, GV, GP, GM. So this denominator is sometimes called as characteristic equation. So instead of using all of the transfer function, we just focusing on the denominator, which is characteristic equation. So for standard block diagram, you have 1 plus GC, GV, GP, GM equal to 0. Let's say you have another form of block diagram. So in this case, you have the GIP. So for this GIP, it will change. The present of GIP ultimately change your final equation. So you get this kind of equation. So for this part, again, we take a look on the denominator. So this equation by inclusion of GIP, your final equation become this. So you just include the GIP inside the characteristic equation. Other than that, remain the same. So normally in our case, we just use two block diagram to avoid further confusion. Either we use the standard or this one. So there will be two. How to know which one to be used? You take a look. Either they give the information about transducer or not. No information about transducer indicate that standard block diagram will be used. If they mention the information of transducer, you should use this kind of transfer function. So that how to differentiate. So since we want to consider the general stability, then we just use the characteristic equation. So for this part, we have the characteristic equation like this. So what we need to do next is to substitute whatever the value of the GC, GV, GP, and GM. So based on that, we expand the equation and try to find the roots. So based on this, we may get this kind of expansion. So From this, you can determine what is the root. The root, or sometimes it's called the poles. If you have the negative root, all the root is negative, then your control system is stable, which is good. The one that we desire. If you have positive root, automatically the system become unstable, which we do not prefer. If you get the complex root, still this contribute to the oscillatory response. Negative complex roots, that means you get still considered as a stable, although it is oscillatory. If you have all the root, real root, that means no complex root, then there will be no oscillation. So this is some of the explanation about the root that you may get. So this is the kind of the response, the potential behavior based on the root. So they say you have negative real root, you can see negative real root located on the left hand side of the axis. It will provide the steady state response, which is this one is considered okay, stable system. If you have a positive real root, then it is located on the right hand side. This you may get the transfer function, which is this one is unstable. We don't want. In some cases, you may get the complex number. So when you have negative complex number, it will be located on the left hand side. Then you still get the stable response, but oscillatory. This oscillatory coming from the complex root. That means you have complex number inside your root. So still this one considered stable system. Only we prefer smooth response without the complex number. And lastly, if you have positive complex root, this one not only you have the oscillatory, but it become unstable. Unstable means you don't reach the steady state. So this is the explanation on what happens if you have negative or positive root and complex number or real root. Complex number will contribute to the oscillatory. Positive root will become unstable. So this is the concept of the stability based on the root. So here what we want to observe is based on the root stability criterion. So I believe if you use the new textbook, the fourth edition, you don't have this kind of subsection. So I hope you can refer to the slide for the formula itself. This formula is available in the third edition, but the current edition, I don't think it is available. So I hope you can give your focus on this topic to have a clear understanding on the root criterion. So first of all, here the step is involving the expansion of your characteristic equation into polynomial form. So remember that we have 1 plus GP, GV, GC, GM. 1 plus GP, GV, GC, GM equal to 0. So you need to substitute the GP, the GV, the GC, the GM, and then try to expand it. And you rearrange it based on the polynomial form. Polynomial means in this case you arrange the term according to the S power. Sometimes you will have the S power of 3. You rearrange it S power of 3, S power of 2, S power of 1, and so on. So this is what it means by the polynomial form. Once we get this kind of the equation, then check the coefficient of your S. So if any of the coefficient A0, A1, A9 are negative or 0, then at least one root of the characteristic equation lies in the right half plane. So if the coefficient is negative, this contribute to the positive root. Negative coefficient contribute to the positive root. So when you have the positive root, that means automatically the system is unstable. So no further analysis is needed. If all of the coefficient are positive, then we need to construct the root array. So you need to have a further analysis if your all coefficient are positive. So we will construct the root array like this, where you have the row 1, 2, 3, 4, and then the AN here, AN2, AN1, AN minus 3, AN minus 4. This one is your coefficient. And the B1, B2, C1, C2 can be obtained from the following formula. So I believe this formula is not available in the textbook. So if you don't have the textbook, the 4th edition textbook, then you can refer to this note. Because in the final exam, you can refer the notes. So that means you can refer this kind of formula, where the B1 is obtained from the following formula. The B1, the B2, C1, and C2. The location of B1 and B2 is on the row number 3 as well as row number 4. So in this case, once we construct all of the transfer function, how to check the stability? First, we take a look on the first column. Based on the arrangement, the first column must be positive. If one of the element is negative, then automatically the system become unstable. Automatically the system become unstable. So this is the requirement. We just check the first column of it. So the first column is here. This is the first column. If one of the first column, the value is negative, automatically your system become unstable. So you don't need to do further analysis. If not, then we can do the further analysis. So for this part, let's take a look on the simple example here. So let's say in this case, we have the GP. The GP equal to 8 over S plus 2 power of 3. The GV equal to GM equal to 1. The GC equal to KC. So first step is expanding the equation. So we use the 1 plus GC, GV, GP, GM equal to 0. So we substitute the GC equal to KC. 1 equal to GV. The GM equal to 1. And lastly, for 8 over S plus 2 power of 3 is your GP. So we include one by one transfer function inside the characteristic equation. Once we insert all of the transfer function, then we do the expansion. So based on the expansion, we may get S plus 2 power of 3 plus 8 Kc equal to 0. So we expand the equation, then we rearrange according to the S order. So here you can see the S power of 3, the higher power of the S will be 3. And then you have 6S plus 2, 12S, 8 plus 8 Kc. So in this case, once we rearrange the equation according to the polynomial, then we check the coefficient, either it's positive or not. So here, the S plus S power of t has the coefficient of 1. This 6, this one 12 is positive. What we don't know is this 8 plus 8 Kc, positive or not, because it depends on the value of your Kc. So we cannot determine either this system is stable or not. So you require further analysis. So based on that, we can rearrange the loose array table, where in the row 1, here in this case, we have the following equation. So if we recall, this is our equation. So since the higher power, S power of 3, so that means you have A3. So this one A3, this one A2, this one A1, and this one A0. So we relocate where the S power of 3, we relocate at the row. We just take the value of your coefficient. The S, we left it behind. We don't use the S in the table anymore. So you have 1 over there, 6 here, and then you have 12, and lastly, A0, 8 plus 8 KC. So that is the arrangement of your row 1 and row 2. And lastly, we complete the first row number 1 and row number 2, we go for the row number 3, where the row number 3 is based on the B1. B1 in this case is obtained from the formula. So this is the formula for the B1. So we have the B1 here. How to use? In this case, you have a n minus 1. Remember that in this case, the n equal to 3 is based on the S power, the highest S power. So you have the S power of 3. So that means your n equal to 3. This contribute to the B1 equal to an minus 1. So an minus 1, A3 minus 1. So you get A2. A2 multiply with the an minus 2. 3 minus 2 is 1. A2 multiplied by A1 minus A3, A0 divided by A2. Again, the n represent the highest power of your S. So for this part, based on the polynomial form, the higher power of the S will be 3. So the n equal to 3. So we just substitute n equal to 3 inside the equation. You get A2 multiply with the A1 minus A3, A0 divided by A2. So what is your A2 here? This is the location of your A2. So this A2, this is A1, A3, A1, and A0. So based on A2, A1, you get 6 multiplied by 12 minus 1 multiplied by 8 AKC divided by 6. So where the value of the B1, you have this minus this divided by 6. So you expand the equation. So this become 6 multiplied by 12 is 72 minus 8 minus 8 KC. So you get 72 minus 8 is 64 minus 8 KC divided by 6. So this is your B1 value. This B1 located at the row number 3. And for the C1, we use the similar formula where we have the B1 8 plus 8 KC minus 6 multiplied by 0 divided by B1. So for this part, 6 multiplied by 0 becomes 0. B1 can be cancelled. That's why you get 8 plus 8 KC. So the location of the C1 is based on the 8 plus 8 KC. So this is the thing that we need to construct. So we complete the row number 1, 2, 3, and 4. So now to follow the system to achieve the stable response, then we need to take a look on the first column. So this is our first column. According to the stability, all elements in the first column must be positive for achieving the stable response. So number 1, row 1 is 1. Row 1 contain number of 1. So this one is stable system. Row number 2, you get 6. Still positive, stable. Row 3, this one we don't know the value because KC is unknown. So what we know is 64 minus HKC must be greater than 0 to ensure this element become positive. When you set greater than 0, automatically the system become positive. That's why we put greater than 0 to find the range of KC. So 64 minus 8KC divided by 6 greater than 0. So we rearrange it, 64 greater than 8KC, then we get 8 greater than KC or KC less than 8 for the first range. So this range ensure the row number 3 become positive. And lastly, for row number 4, you get 8 plus 8KC. So 8 plus 8KC, we set greater than 0 to ensure you get this positive value. So based on this rearrangement, 8 plus 8KC greater than 0, then we rearrange 8KC greater than negative 8. So we know that KC greater than negative 1. So this represent the row number 4 condition to ensure you have a positive value. So since we have two range, KC less than 8 and KC greater than negative 1, so you can combine the range. In the end, the overall combination is like this, negative 1 less than KC less than 8. So this to ensure you get the positive response. So this means based on this, the KC value must satisfy this range for achieving stable response. So it's like that. So this is how you can determine either the process is okay or not. Alright, so this is the further example. I think you can refer it later on. So that's mean in this case, there will be two items that we need to investigate. We need to ensure for achieving good response of your controller. The first one is the offset. So we want to make sure our process reach 0 offset. And also we need to obtain the stable system. How to obtain the stable system is by constructing the Rules array calculation like I show here. So any question from all of you regarding the stability? Okay, we can see the mood is little bit low currently. So I think the rest of it you can refer to my notes. And of course, I will provide further tutorial for you to complete in order to enhance your understanding. So I let all of you to have a revision on this topic. And if you have further question, of course, feel free to contact me for consultation. So I think that's all for our class today. Again, thank you for your kind response, for your cooperation in this class. I see you next Monday. Thank you very much. And class is dismissed.
Thank you,
Thank you.
Doctor.
Thank you, doctor.
Thank you, doctor.
Thank you,
Alright,
doctor.
thank you, doctor.